Hi everyone, in this video we're going to look at section 26.3, volumes by integration. Volumes by integration. In the previous section, 26.2, we found area under a curve, area between curves using integration. Now we get to do some pretty cool stuff and turn that into a volume. And what we're going to look at first is called the disk or washer method. Okay, and it's pretty cool how it works. So let me draw myself some axes here and a little function, and we'll say y equals f of x. And what we do is we take using integration, we take this little slice of a rectangle that in the formula with an integral is represented by that dx, but we take our little slice of a rectangle and we ask the question, well, what would happen if I took that rectangle and ultimately the whole region and revolved it, spun it around, revolve about is the word we use, around basically, the x-axis. Okay, we take that rectangle, spin it around the x-axis. So if you can kind of envision that going on there, what is created is a really, really thin circular disk, hence the name disk method. We'll get to washer a little bit later. And that disk is round, and so it basically is a circle when it spins around the x-axis. So this involves the formula for the area of a circle, which is pi r squared, right? That's the formula everyone should know. Area of a circle is pi r squared, and we'll see how that comes into play in the formula. But if you add those little disks up, which we do with integration throughout the whole region, and spin that whole region around the x-axis, and let me see if I can kind of draw this here. So we would have this guy down there also. I'm drawing just a little sketch here. The disk itself, let me go blue. The disk itself spins around the x-axis. And over here, this guy spins around the x-axis like so. We get a region that has volume, and here's my function. It's not really the function down there, but the other end of the region. But it has a volume, and we add up all of those really thin rectangles using an integral, which is pretty cool. So using an integral, just by using a different formula, we can find a volume of something in 3 dimensions. And the formula that we'll use for the disk washer method around the x-axis is v equals, because we're finding a volume, pi times the integral from a to b, those would be the bounds of your region, wherever it starts and ends, of the function f of x squared dx. Okay, so that's the formula. Where does all of that come from? Right? Well, at that rectangular region, the thickness of that rectangle, that's represented by the dx in the formula, the really thin rectangle. The height of that rectangle is right up here on the function, right? So the height is the f of x, and it's squared because of that formula for area of a circle, a equals pi r squared, right? We have our pi here, we have our radius here, squared, and then we add them up over the whole region. That's the bounds of the integral, and then the dx represents the thickness of each really, really thin slice. So that's kind of how that formula works, and ultimately we just need to know how to substitute into it. So let's take a look at our first example here. Find the volume when the region between y equals x squared, x equals 2, and y equals 0 is revolved about the x-axis. And I like to sketch these, and you could use your graphing calculators to sketch them. That's fine. Sometimes it's better just to draw a rough sketch by hand. Y equals x squared is a parabola. X equals 2 is a vertical line. Let me space that out a little bit more. 1, 2. X equals 2 is a vertical line. And y equals 0 is the x-axis. That's the line y equals 0. So the region that we are looking at, that we're finding, that we're spinning around the x-axis, is this blue kind of triangular region, but it's getting revolved around the x-axis. So think about what that would look like, that actual shape, right? It would be almost like I don't know, it would be almost like a filled in top when that spins around, because this comes down around here, spins around, or maybe like a mega horn, or what are those called? A blowhorn that like cheerleaders use, but it comes to a point instead of like something that you could actually talk into. So that's what our region looks like. So let me rewrite the formula. V equals pi times the integral from a to b of f of x squared dx. All right, so let's see what we need to substitute into that. We have pi. Our bounds from our region, it starts at 0 and ends at 2. That's where I need to add up those rectangles along the x-axis. So my bounds are from 0 to 2. And the function that I'm integrating, my rectangle, the height of my rectangle in that region is determined by the y equals x squared graph. So x squared, but then there's the squared in the formula, dx. All right, so we'll simplify this integral first, 0 to 2. X squared squared is x to the fourth, dx. And then when I take my antiderivative, that's not a nice looking pi, there we go, times x, well, I don't need a parentheses there, times x to the fifth over 5, and that gets evaluated from 0 to 2. Substitute in my bounds. 2 to the fifth is 32, so this will simplify to 32 pi over 5. And we could get that in decimal form, but it looks pretty clean like that. All right, so that 32 pi over 5, we don't typically write the units here, but that is technically a 32 pi over 5 cubic units for the volume of that region. Now, I'm sure as soon as I started talking about this, you were all thinking, what about the y-axis? What can I revolve around the y-axis? And the answer is absolutely yes. Of course you can revolve around the y-axis. What's different about it, though, if I'm spinning around the y-axis, let's say my function looks like this, and I want to revolve it around the y-axis, well, what would that rectangle look like to form a disk? Right there. There, my rectangle is now aligned horizontally, and I'm adding rectangular slices, cross sections up my y-axis. So my bounds are now going to be with respect to the y-axis. My rectangle is a slice up the y-axis, a dy, and my function, instead of y equals f of x, it's x equals g, some function of, some function of y, x equals g of y. So the formula is very similar. V equals pi times the integral from a to b of g of y squared dy. So minor tweaks and changes when we're revolving around the y-axis, but we still have a volume of a region. All right, so the example that we're going to cover here is right there. And we've got y equals 2x, y equals 6, x equals 0, and we're revolving that region around the y-axis. So again, similar to the last question, I'm going to draw a rough sketch of this region to get an idea of what I'm talking about. So my line y equals 2x, I'm not really putting much of a scale on here, but my line y equals 2x intersects the x-axis, or intersects the origin, and has a slope of 2. Has a slope of 2. So we'll just draw a slanty line there. Since I don't have a scale, that's okay. This is y equals 2x. Y equals 6 is a horizontal line up here at 6. All right. And then it says x equals 0. Well, y equals 0 is the x-axis, x equals 0 is vertical, and is the y-axis. So this is the line x equals 0. X equals 0. So the region in question here, what we're spinning around, the y-axis, is that region, and we're spinning around the y-axis. So this triangular region here, we're spinning it, revolving it around the y-axis. And this one might even make a better top if you had like this actual shape in front of you that you would make. But things to remember, because I'm spinning around the y, my slices are horizontal, so that's a rectangle that I try to draw there, but is a horizontally aligned rectangle, and those are getting added up the y-axis. So my volume formula, pi goes first out in front of the integral. Bounds of the integral are from 0 on the y-axis up to 6 on the y-axis. And how is that slice formed? Well, it's the line y equals 2x here, but it needs to be x equals x in terms of y. X equals half y, 1/2 y. And that is what goes here. It's my function of y, 1/2 y squared, d, that looks like an x, but it's supposed to be a y. There we go. All right, so we'll rewrite this, rewrite our 0 to 6, 1/4 y squared when you square that parentheses, dy. And now I can take and do my antiderivative. So the 1/4 kind of tags along, y cubed over 3. I could have just written that as y cubed over 12 if I wanted to. 4 times 3 is 12. There, that looks better. And that gets evaluated from 0 up to 6. Substitute in my 6. V equals, whoops, what am I doing there? This equals pi over 12. So I'm multiplying the 4 times 3 right there. And then it's 6 to the 3rd power. And then minus 0. I'm just writing it down with this one to emphasize that my bottom bound gives me 0. Then 6 to the 3rd power is divided by 12 is 18. And then I leave my pi on there. And that represents the volume of that triangle, but spun around the y-axis, forming that 3-dimensional shape. Spin it all the way around. In our next example, we're going to take a region formed by a parabola and a square root function and revolve it around the x-axis. And what makes this one a little bit different is we're going to have to figure out a little bit more carefully what the bounds of our integral are. So I will start out with a sketch of this region, and my square root function, y equals radical x, does that, y equals root x, and my parabola, it does this. And I'm only going to draw part, well, I'll draw the rest of the parabola. It does that. There we go. And the region enclosed by those two curves is this green region right there. And we can see this looks a little bit different. It brings back things from the previous section where there's like a top function and a bottom function. And also, you know, what are the bounds of my integral? As I zoom in a little bit here, if I draw my rectangle in there vertically this time, because I was told that we're spinning around the x-axis. The x-axis is right there. And there's my y-axis. As I spin that around the region, there's the rectangle. There's like a hole in it. If we try to draw this disc here, the disc has a bit of a hole. There we go, and there we go. Looks almost like a donut, or the name from the previous slide. It's a washer. Okay, so there's my very well drawn 3-dimensional washer in this problem. Okay, the first thing that I want to focus on, though, before we'll talk about the changes with the washer, is what are the bounds of my region? And so as I add up those rectangular slices through the region, right, they end right at this x value right there, all right? And how do I find that? Well, it's where the curves meet, where they touch each other, where they intersect. When is x squared equal to the square root of x? Now, you might be able to, like, look at that and think and figure out when a number squared is the same as the square root of that number. It also happens over here. 0 squared is 0. The square root of 0 is 0. The other point where it happens is at 1. You could just use the solver function in your calculators if you weren't sure, or if you had something that was more complicated, but that is an x value of 1 right there. So what changes in this problem, other than finding that, is the way we substitute into our formula. Because we have a top function and a bottom function, it's going to look just a tiny bit different. Okay, so we still start out with v equals, pi comes out in front, integral from a to b is from 0 to 1, and I'm going to go back to my picture now, and this top curve, the top of the region, is my square root function, and that goes first. The square root of x squared. And then the bottom of the region is the parabola, which is x squared squared. Now, notice what I did here is I made them separate radius squareds, right? So it's top function squared minus bottom function squared. It would be wrong to write it this way, parentheses radical x minus x squared, close parentheses squared. That is incorrect. Correct is the way that I wrote it there in blue. All right, all of that I'll put inside of a bracket and write my dx after it. Okay, that's the setup. A little bit more involved with this one. So let's go v equals. Keep going with solving it. I'm not going to take the integral yet. I got to simplify first. My radical x squared is just x, and x squared squared is x to the fourth dx. Now I can take my antiderivative, pi times x squared over 2 minus x to the fifth over 5, and that gets evaluated from 0 up to 1. We're almost done here. We've got our substitution next. So this is top bound is 1/2, because when you square 1, you get 1, minus 1/5. Oops. Minus, oh yeah, that is right. 1/5, because when you take 1 to the 5th power, still 1, so 1/2 minus 1/5. And then the bottom bound is still 0 when I plug that in. Simplifying, 1/2 minus 1/5, 1/2 is 5/10, 1/5 is 2/10, and what you end up with is 3 pi over 10. And that would be cubic units representing the volume of that region. Pretty cool stuff here. Now, you also might be thinking, well, if I can spin around the x-axis or the y-axis and make disks that way, can I find volumes using any other shapes? I'm sure you are absolutely thinking that. And the answer is yes. Instead of having a disk washer method, we also have what is called a shell method. And when it comes time for a test on this, I'll be really specific in how I want you to set it up. But the reason that we have this in calculus is sometimes one approach is better for a certain region than another approach. Sometimes one results in an easier integral to evaluate. Sometimes one results in an easier integral to set up. Okay, and so what this shell method looks like is, let me draw my axes here. And let's say I have some region that looks like this. This is my y equals f of x function, and I'll end it right here. So here's my bounds from A to B, and let's say I want to spin it around the y-axis. So there's my y-axis. I want to revolve that region around the y-axis, only this time I'm going to force myself to draw a vertically oriented rectangle. Now, if I had drawn that rectangle horizontally, which I could have, it would have, the only difference is it would be, it would still be a disk. It would still be a disk. But in drawing it vertical, what happens as I spin that vertical rectangle around the y-axis? And you can try to visualize this. That's a little too far. Let me try that again. If you spin that around, what kind of image does that, what kind of shape does that produce? Okay, and this is why it's called the shell method. I'm always better at drawing that part than I am at drawing it coming around the front, so bear with me here. There we go, and there we go, kind of, on that one. Okay, so that's our what's called the shell method, and I'll have a video in Blackboard that will hopefully give a better picture than I am able to draw. But that's what's going on here. So that's our shell method, or that's what the shell method looks like. So we force ourselves to have our rectangle oriented the other way, and then it ultimately it produces this shell of volume. And so what does that do to the formula? So the other formula was pretty straightforward. Pi r squared, pi times the function squared. So our formula here, I'll write it down and then kind of explain where things come from. In this one, it's v equals 2 pi times the integral from a to b of x f of x dx. And you may be thinking, oh, whoa, that formula looks much worse. Really, the only difference is instead of a pi, there's a 2 pi. And instead of f of x squared, it's x f of x. It's pretty similar in terms of like degree of difficulty. All right, but where does everything come from? So the first thing, the easiest thing to see, I think, is the f of x. That's the function. So at this point right here, at that point right there, at that x value, the height of that rectangle is determined by where I am on f of x, on the function. So that represents the height of my shell, okay? And then the 2 pi x is the circumference of that shell, the circumference of that slice. You've worked with formulas before. C equals pi times diameter, or 2 pi times the radius. That's the formula for the circumference of a circle. So the circumference of our shell is the 2 pi x, x being the radius of the shell, the distance away from the origin in this case. And then the dx, similar to before, is the thickness of the shell. So that gives us the volume of this one single shell, but in evaluating the integral, we get the volume of the whole region in 3 dimensions. In our next example, we're going to go through one where we use the shell method, and we're taking y equals 4 minus x squared, revolving it around the y-axis, and we're just focusing on Q1. That means quadrant 1, the first quadrant. Okay, so sketching this picture looks like this. 4 minus x squared, again, you can check in your calculator, is a parabola that's up here at 4, comes down to the x-axis at 2, and this problem just says in quadrant 1, so I'm only sketching that part of the parabola, although technically it also comes down like that. But we're spinning this around the y-axis, and we're using shell method, so that means that I'm going to have a vertically aligned rectangle that looks like so. There we go. All right, so what's my formula? V equals 2 pi integral a to b x f of x dx. And all we have to do is find out our bounds. Let me highlight here. I need to know what the bounds are and what the function is. By the way, the x in that formula, that stays just a letter x. It doesn't, like, there's nothing to substitute in there. It's just an x. All right, so what are our bounds? 2 pi. What are our bounds of our region? Well, that blue rectangle that I've got drawn in there looks like it starts over here at 0, and I would be adding them up as I get over to 2. So the bounds of my region, 0 to 2. How about that? X function. What is the top of the rectangle? Well, it's my y equals 4 minus x squared, so that goes inside of this parentheses. 4 minus x squared dx. Boom. So we've got our integral substituted into. We'll simplify inside of the integral first. 0 to 2. 4x minus x to the third, because I'm distributing that x. So instead of squaring with the disk washer method, we distribute with the shell method. And now I can take my antiderivative, 2 pi tags along, 4x squared over 2 minus x to the fourth over 4, and that gets evaluated from 0 up to 2. V equals 2 pi, parentheses. Top bound, plug in my 2. Oops. That 4 divided by 2 is just 2x squared, so 2 times 2 squared minus 2 to the fourth over 4 for the top bound. And then the bottom bound, double check quick, still gives you 0. Then, let's see, when we do the arithmetic here, 2 pi, 2 squared is 4 times 2 is 8. 2 to the fourth is 16 divided by 4 is 4. 8 minus 4 is 4 times 2 pi, 8 pi. Again, use your calculators. You know what to do here. But that represents the volume of that region. So what would this guy look like if this were, actually going back to my picture over here, my graph, if this were revolved around the axis? Well, we'd have some three-dimensional looking, I don't know, would it be like a bowl? Oops, that shouldn't go over that far. So this would come down here. This would come out there. Oof. There we go. And then we'll do another one for the whole thing. It would look like a bowl, although it would be a very rocky bowl, and it's upside down, so it wouldn't hold things very well. But I'm thinking it looks kind of like a bowl, but with a rounded top. Now, in this next example, if we take that same y equals 4 minus x squared, and we take the same revolving it around the y-axis, only this time we allow ourselves to use the disk method because that's what we learned first. That's what we're more familiar with. Well, this should be much better, right? Well, let's take a look. If I want to use the disk method, right, my rectangle is aligned horizontally. I've already got that drawn in the picture, but I'll kind of emphasize it there. I have the formula written down on the right. So let's see. Disk method, those slices are being added up the y-axis now. So I know I've got f of x dx there, but I'm pretty sure that I have pi integral those rectangular slices. Again, I'm adding up the y-axis, so my bounds go from 0 up to 4, and it would be incorrect to write just 4 minus x squared because, again, where our slices are with respect to y. We're going up the y-axis for these rectangles. So I need to take that y equals 4 minus x squared and solve it for x. Okay? And if you do that, you have y minus 4 equals negative x squared. And divide by negative 1 gives me 4 minus y equals x squared. And take the square root, and we get x equals root 4 minus y. Whoa. Okay, so that's not terrible. Radical 4 minus y squared, right? Because it's the function squared. Okay, that's doable. When I simplify that, v equals pi integral 0 to 4. Underneath or inside of the radical, or inside of the integral, we have a square root squared, which should cancel each other out. 4 minus y dy. And then I can take my antiderivative, pi times 4y minus y squared over 2, evaluated from 0 up to 4. And then we take and we go pi times, we substitute in the top bound, 4 times 4 minus 4 squared over 2, minus bottom bound. Check it every time just in case, but in this case it gives us 0 as it often does. Not always, but often. So then we say, all right, v equals pi. 4 times 4 is 16. 4 squared is 16 over 2 is 8. And we get 8 pi. Go ahead and check with a few minutes ago in the video, and we got 8 pi in that example. Also, that just confirms that both methods work. They produce the same volume. But sometimes one might be better. Did you think the last problem was easier, or did you think this problem was easier? This next example, I'm not going to spend a lot of time talking about. I will literally just point at a couple things. We take the same equation, y equals 4 minus x squared, and instead, now this time, we're revolving around the x-axis using both the shell and the disk method. In this one, it might be good for you to try to type this into your calculator if you haven't tried doing integrals in your calculator yet. It's not terrible, especially if you're used to doing derivatives and all that. So you can absolutely do the integrals and check your work and things. I still want to see the steps. I still want to see your work, but the calculator is a tool to help you along the way. So I encourage you to try to figure out where everything in this integral came from and where everything in this integral came from, why it's 0 to 2 here, why it's 0 to 4 here, where that came from. So take a look at that, but then try typing them into your calculator. And in terms of the steps, I'm hitting F3 first. That gives me my integrate menu, or that gives me my calculus menu, and then I'm in that menu pressing integrate or 2, so I'll put a comma there. That's just the next step. So I'm pressing 2 in that menu to get integrate. Then I'm typing my f of x, my function, but making sure that I group that in its own parentheses. Then I go, comma, this is an actual comma button that you press in the calculator, x, just like we did with derivatives, another comma, 0, another comma, 2 or 4 or whatever number for your region, and then a close parentheses. So it's F3 to integrate, choose the integrate option, type in the function in its own parentheses, comma x, comma 0, comma 2, 4, 6, number, whatever the other bound of your integral is, close the parentheses. So try that out with these two examples. And again, take the time to investigate where everything in the integral came from. Okay, so now we get to the last example of the section. And first you were wondering, can I revolve around a different axis? Answer is yes. Second, you were wondering, can I find volumes using different shapes? Answer, of course, is yes. Now the last question, if I can revolve around the x or the y axis, can I revolve around another line? The answer is, of course, yes. And we'll do this last example using the shell method and the same equation that we've been working with for these last few examples, and it's y equals 4 minus x squared in just the first quadrant. So that looks like that. This is 4 up here. This is 2 down there, okay? And we're going to revolve around not the y-axis, but we're going to revolve around the line x equals -2. Whoa, look at that line. It's a beautiful line. X equals -2. So that's the line that we are revolving. We're spinning this region. And the region, mind you, looks like this. This is the thing that we're spinning around, the line x equals 2. So there's like a big open hole over there that I'm going to undo. Yeah, this space here is empty dead air space. So we're creating something with a hole in it. So I would encourage you to try to think of what this 3D printed object could look like. And hey, if you have a 3D printer, please make me one and mail it to me. So next I want to draw my rectangular cross section, my slice that I take out of that region, my dx. And if I'm spinning that vertical slice around that vertical line, right, I'm creating a shell. Hopefully, we've done a couple of examples now. You can kind of see how that's a shell there that has a thickness. There we go. There we go. And there. So there's my shell. All right. Great drawing. Beautiful. Okay, so but that's the shell that I'm finding the volume of and adding them up through the region. Let me rewrite my formula from before. V equals 2 pi for the shell method, integral from a to b, x, f of x, dx. And in substituting for our next step, let's think about what's changed, right? 2 pi, those are numbers. A to b, those are at my red rectangle that I drew in there. Has that changed as I added up through the region? Am I still going from 0 to 2? The answer is absolutely still going from 0 up to 2. And then the x in the f of x was the height of the rectangular slice. Has that changed right there? The answer is no. So that's still parentheses 4 minus x squared. Dx, the thickness of the slice, that's the same. What's changed, though, is the radius of that piece, that slice, that rectangle. Previously, green dot here, to the y-axis that we revolved around, right? That was x. Now it's green dot all the way over to the blue line. So I have increased the radius of my shell by, 1, 2, right? And so what that looks like in the formula is that the x is increased by 2. Increased, that's a plus sign, I swear. X is increased by 2. That's the difference. When we revolve around a line that's not the x or the y axis, what we affect is the radius of the slice. And so that's the only change here. And so I encourage you, I'm going to stop the video here because I think I've talked for long enough and you're done with my voice. But I encourage you to type this into your calculator and find out what this volume is. Otherwise, you'll just be left hanging. If you have any questions on this, please send me an email. This is a pretty heavy topic, but super, super interesting. Thank you for listening. Let me know if you have questions.